Section 4, Running a Random Forest Algorithm. Hello. Before running the random forest algorithm, I want to discuss a couple of its advantages. I talked about how a decision tree and a random forest of them work back in video 1.4, but here is some new material. R's random forest package includes the variable importance function varimpplot. When we run it, you'll see how it rates each variable by two measures: percent increase in MSE, square error, and increase in node purity. The idea behind the first is that if this variable is important, assigning other values in place of the current one ought to reduce your accuracy. To be fair, the other values are chosen randomly from the dataset, so they mirror the distribution we're training on. So the first measurement is how much the mean square error increases if the current variable value is switched out for a random other value, and that value is used in the algorithm. Larger increases indicate the variable is more important. The second comes from the goal of a decision tree, to ideally make each leaf pure or consisting of only one outcome. If this could be achieved, the tree would predict with perfect accuracy. Rather, if this could be achieved on new data, on the test set. This is why decision trees will overtrain on the training set by splitting until all leaves are pure, unless restrained. Overtraining will increase purity on the training set, but decrease it on the test set where it counts, so predictions will get worse. This measure records how much those splits, where the target variable is chosen to split on, improve the node purity, summed over all trees and all splits on this variable. A variable which consistently improves purity better than others ought to be an important variable. Don't read too much into the details of the ratings, but a variable which rates high in both measures, and the plot shows how much better it is likely more important for the prediction, which is an important thing to know. Larger data sets, there can be hundreds of variables considered, so it's good to know which ones stand out. When I was starting out in machine learning a while ago, I once worked with a longitudinal data set, meaning a number of questions asked twice, years apart. I was trying to predict from the first set of answers which patients would survive until the time of the second set. My predictions did better than I thought. Most important variable came out as a very obscure one, which really surprised me. It turned out, after some digging, it wasn't in the initial documentation, that this obscure variable wasn't a question anyone had thought to ask in the first question set, meaning that if there was any data in it, it was a great predictor of survival because only survivors got asked about it, and my excellent prediction was garbage. I learned to always check my data set, and if something looks too good to be true, it probably is. Another advantage of the random forest algorithm over many sophisticated algorithms lies outside the realm of mathematics. The end result of your machine learning work will be a story, which will drive action in your organization. This will involve convincing a decision maker who will not understand all the details of your algorithms, yet you must explain clearly why your results indicate the direction the organization should commit resources. A decision tree is nothing more than a bunch of rules written as if statements. If A is less than 17 and B is 12 or higher and C is yes, then we predict this outcome. One such statement for each leaf of the tree. These look solid and unambiguous. Variable importance is another selling point if the variables that emerge fit with the intuition of someone expert in the subject matter. Yes, machine learning is mostly about mathematics, but in my experience, understandable algorithm is more likely to drive action. This dimension cannot be overlooked. I'm always happy to present random forest results when telling my story.